Okay, today we're going to continue with Chapter 1, Relations and Functions. We're going to be talking about Chapter 1.7, Transformations. The idea of a transformation is that we can take a graph and make some changes to it. So what we're going to do is we're just going to create a very standard looking graph. Something that has a recognizable shape that we can practice transformations on. And there's going to be 3 different types of transformations. We're going to look at translations, reflections, and dilations. Translation is simply shifting the graph up or down or left or right or some combination thereof. A reflection is taking the graph and reflecting it over some line. It's also moving the points of the function, but instead of moving all of the points some fixed distance in some fixed direction, we're instead flipping the points across a line. So when it's further away, flip further, just like if you were reflecting across a mirror. And the last one is dilations. For a dilation, we are either stretching the function out or squishing the function in. Of these different things can be represented algebraically. So you can look at a function that is similar to a function that you know how to graph and use transformations to figure out what the graph will look like. Let's call this basic function that we're going to be working with f of x. The way that we've set up f of x, the domain is the interval 0 to infinity, or x is greater than or equal to 0. So we can also look at how the domain of f is affected. Let's begin with some translations, also known as shifts. For a vertical shift, we will simply take the amount we want to shift the function and add it to the end. If we add the value and it is a positive value, then the function will shift upwards. If we subtract a positive value, or alternatively add a negative value, the function will shift downwards. A good way to think about this is that if we add k to one side, the way to balance that out would be to add k on the other side as well. So by increasing the right by k, we have to increase the y values by k. Thus, we will shift the graph upwards by k. For example, if I was to take our standard graph again, which recall is f of x, then we can look at what f of x might look like if it was shifted upwards. If this right here was k, then I would say this is the graph of f of x plus k. We could also consider a shift downwards. This would be the graph of f of x minus k. Notice in each of these cases, the domain has not changed because I've only shifted the function up or down. This may end up affecting the range. We can do the same thing horizontally. The difference here is that since I want to make a horizontal change, which is a change to the variable x, then I will have to add or subtract directly from x. Now, one thing that is not always intuitive is that adding or subtracting from x will have the opposite effect as it did when you added or subtracted on the right-hand side of the equation. In other words, when I'm subtracting x here, I will be shifting the graph to the right, which is the positive x direction. Whereas when I add to x, I'll be shifting left, which is in the negative direction. The reason for this is you need to think about what you need to do to x to counterbalance the k. Since I am subtracting x in the first instance, in order to counter that, I would need to add back to x to balance it out, since both of the pieces are inside the parentheses right next to each other. This is opposed to before, where the thing I'm adding was on the opposite side of the equation from y, so the way to balance it was to do the same thing. Here, the way to balance it is to do the opposite. So again, we'll reprint our standard f of x graph. And we consider f of x minus k. And we also consider f of x plus k. Again, I am adding or subtracting inside the parentheses here rather than outside. And as a result, the shift of the function is in the opposite direction. And again, because the change is made directly with x, it moves to the right, the positive direction, when I subtract, or to the left, the negative direction, when I add. Let's do an example here with a function that has a formula. Let's say f of x is equal to the square root of x minus 2 plus 3. Now, we haven't talked about square roots yet in this class, so I'll just give us the graph for square root of x. And let's call this one g of x instead to differentiate from the f we were working with earlier. The graph of g of x looks like half a parabola, since a square root is the opposite of a parabola. This one here, we've got y equals the square root of x. It goes through a couple of points here. We're going to have the point 1, 1, and the point 4, 2. Notice now that I've got a specific equation for this graph, I need to make sure that I'm labeling my axes and adding a scale back in. It also begins at the origin, 0, 0. What I can do to shift this graph is I can take a look at these pieces. X minus 2 would represent a shift right by 2. And the plus 3 would represent a shift up 3. I know that the first one is a shift right because it is a change that is happening directly to x. X is being square rooted, and this negative 2 is being applied also inside the square root. Whereas the plus 3 is outside of the square root. It's not happening directly to x, it's happening to the entire function. I'm adding 3 to the whole thing, and that will mean I have a vertical shift. Again, the one with x does the opposite of whatever sign we have. The one with y does the same sign, due to the fact that it is on the same side of the equation for x, or the opposite side of the equation. So what that will look like is I will take my function, I will shift it right 2 and up 3. I can simply shift each point. So right 2 and up 3, here, here, and here. Each individual point. 3, 2, or excuse me, 2, 3. 3, 4, and 6, 5. Each of these points, when compared to the original, is right 2 and up 3. And the entire function will look the same as well. The next type of graph is a reflection. So if f is a function, I will reflect it by multiplying by -1. This will switch the sign of each of the coordinates and reflect over one of the axes. And just like before, the question is, do I want to make the change directly to x, which will result in a horizontal change, or do I want to make the change to the entire function that is equal to y and create a vertical change? If I subtract the whole function, then I'm flipping y, and thus I have a vertical reflection. That would look like this. In terms of our example, if this is f of x, then this would be negative f of x. Alternatively, if I made the change directly to x, then I have the opposite kind of reflection, a horizontal one across the y-axis. And to our sample function, f of x will reflect this way, f of negative x. Again, we have this consistent idea. If I make the change directly to x, then that will represent a horizontal change, in this case, a horizontal reflection. Alternatively, if I make the change to the entire function, that will represent a vertical change, in this case, a vertical reflection. Working again with the square root, if I were to take h of x, would be negative square root of x plus 3. Now I've got two transformations. I've got a reflection and I've got a shift. Typically what you will do is you will first apply any changes to x, and then we will apply the changes to y. This means that I should first shift my function to the right, and then I should perform the reflection. Think of this as looking at what's happening to x first, since x is my input, and then working from the inside out. So this will be the original function square root of x. First, I need to shift it to the right 3. 1, 2, 3. And I get square root of x plus 3. Finally, I will need to do the reflection. And recall that this simply means that I am switching the sign of each of my x coordinates. That means that everything becomes a mirror reflection, and this will be negative square root of x plus 3. I've applied the transformations one at a time. First, the translation, then the reflection. And the reason I did it in that order is because you want to look at the changes that happen directly to x first, and then work from the inside out. Finally, we have scalings or dilations. Scale is accomplished when you multiply the function either directly with x for a horizontal scale or the entire function for a vertical scale by some number. We saw the multiplying by a negative performed a reflection, but when the number is anything except for -1, I also will get some shrinking or some stretching. When I multiply the entire function by a number larger than 1, then I stretch it out. We could call that a expansion or a stretch or a dilation by a factor of a. If the number is between 0 and 1, then I might say that is a compression or contraction or a shrink by a factor of 1 over a. So for example, if I multiplied by 1/2, I would say that that is a shrink by a factor of 2. If the number is equal to 1, we've done nothing. If the number is equal to 0, we've made the whole thing disappear, so that doesn't really count. And if the number is a negative number, then all I've simply done is I've combined a reflection with a scaling. So you'll treat it as two separate and distinct transformations. As we might expect, a horizontal transformation in terms of scaling will work in a similar way, but I will instead apply the change directly to x, and the change would work in the opposite way. So again, if I have a number a, and I multiply it directly with x inside of the parentheses, then that will take the function and stretch or shrink it out. Again, directly to x means that if I multiply the function by some number larger than 1, then I will shrink it, whereas if I multiply it by a number smaller than 1, I will stretch it. The opposite of the way it worked when I multiplied the entire function by that number a. Let's do one final example that brings everything together here. Let's suppose that I have actually, let's do one first short example, and then we'll do one that brings everything together. First, I just want to focus on y is equal to 2 square root of x, and compare that to y is equal to the square root of 2x. In this first case, what I've done is a vertical stretch. So we'll recall the original function. Oops, let's get that better to scale. Y equals square root of x. It goes through the points 0, 0, 1, 1, and 4, 2. If I were to take 2 times the square root of x, this is a vertical stretch of a factor of 2. So I'm doubling each y coordinate. That gives me, let's get this nicely to scale, 2, 1, and 4, 4. Excuse me, this is not 2, 1. This is 1, 2. I've doubled every y value while leaving the x values the same. That means that I'm still going through the origin. I've still got the point 0, 0, but each of my other y values is doubled, giving me a graph that has been stretched out vertically. For y equals 2 square root of x, let's again compare the original function going through the origin, the point 1, 1, and 4, 2, and we'll compare this function to 2 square root of x. In this case, remember, since I'm doing a horizontal change and the change is applied directly to x, then the change is the opposite. So this time it's a shrink of a factor of 2. That means that each x coordinate will be halved. So I will have the point 1/2, comma 1, and I will have the point 2, comma 2. I've taken each x value and halved it while leaving the y values the same. Let's look at one final example that combines everything together. Let's say I have y equals to 1/2 the square root of 2x minus 6 plus 4. Now, I see several changes going on here. I see some stretching and shrinking, and I see some shifting. Now, the first thing you're going to want to do when you have something like this is factor out the greatest common factor directly with x. The reason for this is that you will want to make sure that you have the shift identified as happening directly to x, and then the scaling being applied afterwards. So I would like to rewrite this function as 1/2 times 2 multiplied by x minus 3 plus 4. This way I can more clearly identify the translation as being applied directly to x. A stretch or shrink will work the same way when applied to a translated function. So if I were to shift the function and then stretch, nothing would be different. But if I stretched the function first and then shifted it, that would work differently. This is why we apply the shifting first, followed by the stretching. Therefore, I will first identify the shift. Right here, I have a shift right by 3 and up by 4. Then I'll identify the stretching. So this would be a shrink of 2 horizontally, and this would be a shrink of 2 vertically. Again, recall that the part done vertically applies the way we expect it might, where a fraction indicates a shrink, whereas the part applied to x applies the opposite, where a whole number implies a shrink. Therefore, the first thing we'll do is we will apply the stretching and shrinking, and then we will apply the shifting. So let's take the original function square root of x with the points through the origin, 1, 1, and 4, 2. We will make sure to do the shrink. I've got a shrink in both directions. So that means that I'll go through these points of 0, 0, 1 half, 1 half, and 2, 1. Next, I will want to apply the shifting. So I need to go right 3 and up 4. I'll shift each point separately. That means that I will have 3, 4, 3.5, 4.5, and then finally the point 6, or excuse me, 5, 5. Again, we first apply the shift, then we apply the scaling. That was written backwards of what we actually did with the graph here. We first apply the scaling, then we apply the shift. You'll want to always apply the scaling before the shift. And you'll want to make sure the graph is written in such a way for the equation that you can clearly identify the shift. That is, you'll always need to factor first. That's all we have for today. Have a great day.